Welcome back to another explainer. Okay, so today we're decoding the hidden geometry that dictates how we travel across the globe. Look, if you've ever stared at that little in-flight map on an airplane and thought, why is my plane flying in this massive, sweeping curve to get to our destination? Well, you're in exactly the right place. We're going to demystify the Great Circle route, and we're taking it all the way from raw mathematical theory directly into a fully coded interactive map.
So here's the ultimate question. How do we actually calculate the exact shortest path across a spherical Earth? Because when we look at standard flat maps, flight paths almost always look completely distorted, right? They seem way longer, not shorter. But that flat view is just an illusion. Today, we're figuring out how computers calculate these perfect mathematical arcs to find the true, literal shortest distance between any two cities on the planet.
All right, let's dive right into this flight plan. Here's our agenda. First, mapping the Great Circle. Second, finding the vertex. Third, the math behind the waypoints. And finally, coding the interactive map.
Starting off with Section 1, mapping the Great Circle. A great circle route is, by definition, the shortest path between 2 points calculated using a spherical Earth model. Remember that straight line you'd try to draw on a 2D piece of paper in grade school? Yeah, it completely fails when you apply it to our actual planet. To find the true shortest path, we have to respect the geometry of a sphere. It's basically like visualizing a flat plane that slices right through the center of the Earth to connect City A directly to City B.
Now, to make this work in reality, we need a magic number, 6,371. That is the Earth's radius in kilometers. The source code we're analyzing today strictly relies on this constant. Without it, our trigonometry would just spit out abstract angles. But by factoring in 6,371, we're translating those mathematical angles into actual physical kilometers that an airplane can navigate.
Moving right along to Section 2, finding the vertex. Okay, so the vertex is the maximum or minimum latitude reached by our selected Great Circle arc. Put simply, it's the absolute highest or lowest point of the curve on your map. Think of it like the peak of a mountain. Before we can mathematically pinpoint any random waypoint along our flight path, we absolutely have to locate this peak point first. It's the baseline reference for literally everything else we're going to calculate.
Real quick, let's establish the visual language our source code is using here. When we look at the map a bit later in the explainer, the green line is always going to represent our actual Great Circle route. And that red marker? That's going to highlight the vertex we just talked about. Keep those colors locked in your mind. It's going to help you instantly orient yourself when the math gets a bit heavier. Which brings us to Section 3. The math behind the waypoints.
To actually plot a plane's position somewhere along that green route, our source program uses Napier's Rules of Spherical Trigonometry. It is an incredibly elegant framework. We basically use it to calculate a specific waypoint located at a set angular distance, which the code calls sigma, moving away from our red vertex.
I know this looks a little intimidating, but here is the logic building step by step, straight from the underlying JavaScript. Step 1 calculates the new waypoint latitude by multiplying the sine of our vertex by the cosine of our distance. Step 2 figures out the shift in longitude using an arctangent function. And then Step 3 just adds that shift to our original point. So functionally, you're just taking a starting point, factoring in an angle and a distance, and boom, it gives you a brand new exact GPS coordinate.
You might be thinking, why bother with all these sines and cosines? Well, because standard flat math completely fails to account for the Earth's curvature. Honestly, if you tried to use regular algebra to fly a plane across the Pacific, you'd end up hundreds of miles off course. Spherical trigonometry, on the other hand, accurately plots these waypoints by wrapping the math around the globe, flawlessly anchoring everything back to that vertex.
And that beautifully sets up Section 4, coding the interactive map.
To actually build this visual calculator, the developer used a pretty standard but super powerful tech stack. We're talking HTML, CSS, and JavaScript for the logic and interface. For the map rendering itself, it pulls in a library called Leaflet, overlaid with OpenStreetMap tiles to give us the real-world geography. The code even includes some awesome preset routes like Seoul to Paris or New York to Tokyo, so users can instantly generate these complex mathematical paths.
Okay, so here is where all those abstract pieces finally snap together in the interface. We're plotting a route from Seoul to Paris, and right away you see that sweeping green Great Circle route. Right near the top, there's our red marker, the vertex, the highest latitude of the journey. And sitting just a little further down that green line is a blue marker, which is our precisely calculated waypoint.
Now what's really amazing is that the blue waypoint marker isn't just a static dot. It's totally dynamic, reacting to that distance angle slider at the top. When you slide that bar, changing the value of our angle sigma, the JavaScript instantly feeds that new angle right back into the three-step Napier formula we just walked through. In real time, the browser recalculates those sines and cosines, and you literally watch the blue marker glide perfectly along the green route, moving away from the red vertex. It is, quite literally, spherical trigonometry made visible.
It kind of makes you pause for a second, right? If just a few lines of JavaScript and some spherical trigonometry can flawlessly map the perfect curve of a 10,000-kilometer flight, what other invisible mathematical paths are guiding our daily lives? From the GPS in our cars to the literal data packets routing to our phones, we are totally surrounded by hidden, elegant geometry. I really hope this explainer gave you a whole new appreciation for the numbers guiding our skies. Thanks for hanging out with me on this one, and hey, keep looking for the math behind the map.